the motherboard fried the CPU. So we will definitely not use any CPU until this short is gone. I guess I overheated them. At least I don't see any holes. When I do inject, they started to heat up. Hey, I shifted my focus to the display output. Okay, unbelievable. Hi everyone, today on the bench we have ASUS ROG STRIX B650E-F gaming Wi-Fi. And this one comes with a serious claim. The customer says the motherboard fried the CPU. According to the report, the system suddenly powered off and never came back. After testing the processor in another board, it no longer works, which raises the main question: did the motherboard actually damage the CPU or did something else fail first? With AIM5 platforms, a CPU failure is rarely random. If a processor is damaged, it's usually the result of a power delivery issue, overvoltage, a shorted MOSFET, unstable V-core, or a failure in the VRM control circuit. So in this repair, we won't just be looking for where the board doesn't post. We'll be investigating whether there was an abnormal event on any of the critical rails, before even thinking about installing a test CPU. So if this board really killed the processor, there will be evidence. Let's find out what actually happened. Okay, let's measure the resistance on main power rails. The first is 3.3 volts, and so I need to show the multimeter. Here we go. Okay, 3.3 volts, and we have 98 ohms. Okay, it's kind of less, I guess. I guess this is not shorted, but it's very low. What about the 5? 1.8 kilo ohms. Okay, 5 is good. What about 12? 12 volts from the ATX power. We have kilo ohms. Okay, minus 12 kilo ohms. 5 ESB. It's 5 volts standby power. And we have 10 kilo ohms, which is okay. Now let's see the CPU. 12 volt CPU. Okay, kilo ohms. Then we measure 12 volts to V core. Oh, here we go. It's shorted. So this is why this motherboard can fry the CPU, because 12 volts goes directly to V core. I pretend that one of the MOSFETs from the V core or SoC rails here are damaged. So this is interesting. Like, is it also shorted to SoC? And I guess yes. Okay. So we will definitely not use any CPU until this short is gone. And what we need to do is to disassemble the board and to make an inspection of the VRM area. Let's do it. Okay, let's inspect within the microscope the VRM area over here. Well, actually, everything looks fine here. At least I don't see any holes in the PCB. So I guess what we need is to inject 1 volt and to see which MOSFETs will be heated up. Alright, so we're now going to connect to the ground. I forgot that we have 12 volts to V core, so we need 12 volts here. Okay, and our V core is going to be here, right? Yes. Okay, so let's see what is heated here. Okay, so I'll inject right here. And I have 5 amps. Okay, my connection is actually heating here. Okay, I see those 2 MOSFETs. Okay, so I guess that I found that those 2 MOSFETs are probably the candidates number 1. Like when I do inject here, so they started to heat up, as you see. So we're gonna remove them and see if the short is gone. Okay, now the board is still hot. We need to let it cool down a bit. And after that, we'll measure resistance. So, and we still have a short. Okay, unbelievable. So there is more MOSFET. I did one more sweep with the thermal camera and found another culprit in the V-core. This MOSFET was just barely leaking heat, nearly invisible to the eye, but a definite red flag. Even at low temperatures, a power stage dissipating heat like this is a sign of internal damage. Let's remove the third MOSFET here as well. To confirm the removed MOSFET was definitely damaged, I measured the resistances, and sure enough, the input was dead shorted to the output. Now let's see if we have a short. Go here and here. See, no short anymore. We have normal kiloohms here, and to ground, the mega ohms. So that was the problem. Okay, finally, I got a donor board for the MOSFETs. This is 15 SIC 659. Same amount as the amount of phases of the VRAM on this motherboard. This is a Tough Gaming Z690 plus Wi-Fi. This motherboard has a damaged CPU socket, so we will use it as donor board and just salvage the components from that. Let's do it. So we did solder it in new MOSFETs, and we need to check, very important, the resistance between each power lines to be sure that it's safe to put in the CPU to this motherboard. So we will have 12 volts here, and we need to measure SOC resistance, and we need a multimeter here. So those two are SOC, and we have mega ohms here. It'll be the same. To ground, and we have 79 ohms to ground. Do we have any kilo ohms? Oh, 79, yeah, 80 ohms. And the V core to ground is 51 ohm. And 12 volts to V core, mega ohms. 12 volts to SOC is also mega ohms, which is good. Okay, now the resistance on these caps, mega ohms. This cap, well, so every cap here actually should be measured, just not to not have lost any short if it's present. So 1.8 kilo ohms here, going to be 2 mega ohms here. Okay, what else? So SOC to V4, kilo ohms as well. And that's it. That's what we need to know. Let's try to power it on. and to see if we will have any change. Over on, we have 143 milliamps right now. So we're pressing. Let's connect the capture screen here. Okay. Let's see the pause screen here. Pressing the power button. (1.7). We have the DRAM LED here. The board stalled during the power-on sequence with a constant DRAM LED. Probing the phases revealed that some were missing the PWM signal. I was concerned that I had overheated the MOSFETs and damaged the internal logic. Since my donor board still had 12 MOSFETs, I decided to give it a try and replace the MOSFETs again. As you can see, the motherboard is on the rework station, more specifically on the bottom preheater, which I use for more complex cases. As you've probably already guessed, the SoC MOSFETs are not working properly, and I suspect I may have overheated them during soldering. So this board has large copper zones, which makes it very difficult to properly melt the solder under the MOSFETs. Because of that, I may have applied too much heat from the top side. So this time, I want to try soldering them again using less heat and a more controlled approach. So let's give it a try. Okay, 144 milliamps, pressing power button. Oh, 2 amps. 2.2. Okay, CPU. This is a good sign, actually. VGA. Okay. It looks like we are booting. Let me connect the capture screen real quick. Pressing the power button. VGA, and come on, will we have a pause screen? 41 watts. 3.3 amps. Come on. There was still no pause screen, so I grabbed the oscilloscope and started checking each VRM phase one by one. Everything looked normal except the second SoC phase, which had no PWM signal at all. Naturally, that became my main suspect, but no matter what I tried, the PWM never came back. That's when it hit me. This phase might not actually be the problem. It has been a couple days since I tried the motherboard to get posted. You know, I was deep in weeds troubleshooting what I thought were that SoC phases. I even went as far as swapping out several power stages from a donor board, but here's the kicker. I found out that ASUS uses DG+ power control in the BIOS. This feature automatically limits the number of active phases during light load or idle period for power-saving reasons. Technically, the VR controller is putting those phases into a 3-state PWM mode. In this state, the controller puts its output into high impedance And the internal logic of this SIC 659 series chips pulls the PWM pin into a window usually around 2.3 volts, which tells the chip to turn both the high side and low side MOSFETs off. So the phases were not dead, they were just slipping to save energy. With that mystery solved, I had to figure out the real reason we still had no post screen. And after a close inspection, I found out the culprit. So, a physically damaged HDMI port. The damage was preventing the hot plug detect signal from reaching the processor. It's a classic mistake. We got so focused on the complex silicon like those 50 amps VR power stages that we forget to check the basic physical connectors. If the board doesn't see a monitor because of a broken pin in the post, it's not going to finish its handshake or post screen. So, to test the theory, I bypassed the HDMI port entirely and connected my monitor via DisplayPort on the same integrated graphics output. And just like that, we have a successful post screen. The board is alive, the SoC phases are firing up as needed, and the BIOS is fully accessible. The big lesson here, always check your BIOS power settings like ASUS DG power control before assuming a phase is dead. On high-end AM5 boards, advanced phase shedding logic is designed to put those 50 amps power stages into 3-state PWM mode during light lows or idle periods to save energy. So, and most importantly, always check your physical ports. A tiny band pin in an HDMI port can block the hot plug detect signal, making a perfect healthy board look like it has a major system failure. To make sure this repair is 100% professional, we will be replacing that damaged HDMI port with a brand new connector before returning the motherboard to the customer. Thanks for following along on this journey, and if this helped you troubleshoot your own board, hit that like and subscribe button, and I'll see you in the next one.